Hello everyone, my name is Rajalakshmi Chandrasekhar. In the previous video, I have given you a brief idea of what is Power System 1, why we should be reading it, and what are the prerequisites and so on. So, this is the first video on the topic, and the topic for today is Introduction to Power System. So, here we'll have a brief idea about what is power system actually. So, electrical power system. It is defined as the conveyance of electric power from a power station where the power is generated to the consumer's premises, and this whole process is known as the electrical supply system or electrical power system. So, it is mainly the conveyance of power from the power station to the consumer's premises. So, our electric supply system consists of three principal components. What are those? The power station where the power is generated, the power station where the power is generated. Then we have the transmission line which helps the power to be transmitted. And the last one is the distribution system from where it is distributed to the consumer's premises. So, electric power is produced at power stations, and these power stations are located at a favorable places, generally which are quite away from the consumer. So, just by a single line diagram if I show, so the generation of power is somewhere here and the distribution is somewhere here. So let me write this as D. So it is generated from a very far off place from the distribution point of view. And so what happens, the power that is generated in the power station is to be transmitted over a large distance to the load centers with the help of the conductor. So the conductor that is joining the power station to the distributor or the consumer, this conductor is nothing but it is doing nothing but helping us to transmit the power generated in the generating station to the consumers. So finally, after it reaches this section, here it is distributed to a large number of small and big consumers through distribution network. So power system is basically nothing but the process that involves generation of power, transmission of power, and distribution of power. So here you can see this diagram. It represents a typical AC power system. This is a single line diagram of a typical AC power system. So here, first of all, this is the generating station. So the generating station, here the voltage is generally of 11 kV. The generation voltage in the generating station is mainly 11 kV. Before the transmission of electrical power is stepped up into 132 kV. So from the diagram you can see that here the generation station, the power generated is of 11 kV. It is then, you can see here there is a step up transformer which steps up the voltage from 11 to 132 kV, and then it is transmitted. So up till here it is generation. Then as you can see, this is primary transmission and secondary transmission. So up till here it is transmission and the remaining is the distribution section. Okay, so in the generating station, what happens? The generated voltage is of 11 kV, and before transmitting it, the voltage is stepped up from 11 kV to 132 kV with the help of a step up transformer. Okay, then next comes the primary transmission. So the voltage in the primary transmission is 132 kV and it is transmitted using a 3-phase 3 wires overhead system, and it transmits the power from the generating station to the outskirts of the city, and it terminates at the receiving station. So here you can see the voltage from this step up transformer till this step down transformer is 132 kV and it is known as the primary transmission. It ends when it reaches the receiving station. So in the receiving station, what happens? In the receiving station, there is a step down transformer which steps down the voltage from 132 kV to 33 kV. So secondary transmission voltage is 33 kV. It is also transmitted using a 3-phase 3-wire overhead system and it comes up to the substation. The primary transmission ends at the receiving station and the secondary transmission ends at the substation. So here the secondary transmission, the voltage is 33 kV. So it starts from the receiving station till the substation. So before it enters the substation, what happens? The voltage is reduced. No, not before it enters, at the substation. Actually, at the substation, the voltage is stepped down from 32 to 11 kV using a step down transformer, and then it is supplied. Here you can see there are arrow marks. So it is supplied to big consumers like some industries. 11 kV is given to big consumers like industries. Then comes the secondary distribution, where the electrical power from the distribution line, which was 11 kV, is delivered to the distribution substation. Here you can see this distribution substation has a transformer, distribution transformer, which steps down 11 kV to 415 volt. These substations are located near the consumer locality and they step down the voltages to 400 volt. 3-phase 4-wire system is used for DC for secondary distribution. The voltage between any two phases is 400 volt and between any phase and neutral is 230 volt. So we'll come in details, we'll know about this, why the transmission is used 3-phase 3-wire and why we use 3-phase 4-wire for the distribution part. We'll know all of this in detail. So as of now, what we need to know is that the power system consists of 3 processes: generation of power, which is done at 11 kV, transmission of power, which is done at 132 kV and 32 kV. The primary transmission is of 132 kV, the secondary transmission is of 33 kV, where the power is transmitted from the generating station to the substation. In the substation, the power is stepped down from 32 to 11 kV. So 11 kV is the primary distribution voltage. Again, in the distribution substation, the voltage is further stepped down from 11 kV to 415 volt. So the voltage in the secondary distribution is 415 volt and then it goes to the consumer depending on the requirement of the consumer. So if a consumer requires 400 volt, then the two phases are connected. So if we have a 3-phase 4-wire, suppose we have R, Y, B and N. So if the requirement of a consumer is that of 400 volt, then the consumer will have one phase from R and another phase from Y, and here the load will be connected. If the consumer is a domestic consumer, then it will suppose take a load from B and another load from N, and it will be given to the load. So the voltage for the second one is 230 volt and the voltage for the first one is 400 volt. So 400 volt will get only when we will connect two phases, and we'll get 230 volt when we take connection from a phase and a neutral. So this is a typical AC power system representation in a single line diagram. Next, we'll be seeing that the electric supply system can be broadly classified into. Classification is based on criteria. So first criteria is based on the nature of current, that is AC or DC system. So a power system can be a AC power system or a DC power system. In the previous slide, what we have already seen was a AC power system because the power generated was in AC. and throughout transmission and distribution the nature of current was also AC, so it is an AC power system. The power system can further be classified based on construction as overhead power system and underground system. Then, as I have already told you that three-phase, three-wire AC system is generally adopted for generation and transmission of electric power as it is economical. We use only three-phase, three-wire for the generation and transmission purpose, and we use three-phase, four-wire for distribution of electric power. This I have already told you. Why? That also I have explained. The underground system, here I told you that the power system can be overhead power system or underground power system. The underground system is more expensive than the overhead system. So usually whatever we see around, most of the connections that we see is of overhead type only. So in our country, overhead system is mostly adopted, mostly, not everywhere, for transmission and distribution of electric power. Now, we have already seen the AC power system. Now we'll be seeing the DC power system. Here you can see that the power, the electric power in the single line diagram, you can see this is the generating station. So the electric power is generated as AC and it is stepped up to high voltage by the sending end transformer TS. So TS is a transformer which is stepping up the voltage. As in the previous case, we saw it was stepped from 11 kV and here it was stepped as 11 kV to 132 kV. So suppose this sending end transformer TS is stepping up the voltage generated at 11 kV to 132 kV before the transmission is done. So as it is a DC power system, what happens is here the power that is transmitted is not AC. It is DC in nature. So the AC power at the high voltage is fed to the DC power, the AC power that is generated in the that we get in the secondary side of the sending end transformer. It is fed to the mercury arc rectifier. What is the work of the mercury arc rectifier? It converts the AC into DC and therefore the transmission that occurs here is a DC transmission. That's why this system is known as DC power system. So the transmission of electric power is carried out at high DC voltage. At the receiving end, here at the receiving end, the DC is converted into AC. So here what we get is an AC. How? With the use of this thyratron. What is the purpose of thyratron? The thyratron converts the DC into AC. The AC supply is stepped down here using this receiving end transformer TR and it is supplied to the consumer. So this is how a DC power system works. So here we have the additional equipment that we use are mercury arc rectifier which converts AC to DC and the power is transmitted in DC. Then we have thyratron which converts DC to AC. Okay. So we have already seen what is the difference between a AC power system and a DC power system. Now we'll compare the overhead and underground power system. So as you can see, the comparison of an overhead and underground power system can be done based on various points like the fault location. The fault location in case of overhead line is much more easier because it can be easily visible, but in case of underground system the fault where it has actually occurred is invisible, so it is difficult to find the fault location. The in case of cost, initial cost, if we compare the two systems, it is found there the cost of overhead line is less compared to the underground system, because here no requirement of digging manhole or trench is required. So it is cheaper than the overhead system. But here the initial cost of underground power system or the transmission system, whatever you say, is more compared to the overhead transmission line. So the chance of fault, the occurrence of chance of fault is more in overhead transmission line or overhead power system, because here the conductors that are laid in the overhead is exposed to environment like wind, rain, thunder, etc. But the cables are not exposed to the environment, hence the chance of fault is less in underground system. If we compare from the point of safety, the overhead transmission line is less safe, because the conductors are placed on the towers, and if due to wind or if anything falls on the conductor and it strips off, then people may come in contact with the conductor, and there might be accidents. So it is not safe, but from the point of but from the same point of view, the underground system is safer. The useful life of a overhead transmission line or power system is 20 to 25 years, whereas that of underground system is 40 to 50 years. From the point of view of appearance, the general appearance of the system is not good, because there will be conductors everywhere and it gives a very untidy look. It is very untidy, and the underground system, it is not even visible to our bare eyes. So it is, from the point of view of appearance, it is good. The maintenance cost of an overhead system is less compared to the maintenance cost of underground system. The maintenance cost in underground system is more. So like this, we can compare the overhead line and the underground line based on few more points, like the flexibility of the system, the conductor size, the interference of the line with the communication system, the proximity effect, and the application. So from the flexibility point of view, which one is more flexible? Obviously the overhead line will be more flexible, and the expansion in case of overhead line will also be possible very easily. But underground systems are not very flexible, and the expansion cost is nearly equal to the new erection. Like if we already have a system and we plan to expand it, then it will be equally costly as we design as was the cost for designing a new system. Conductor size, there are size of the conductors are smaller compared to the underground system. Interference of communication line, here in case of the overhead transmission line, there is a possible cause of electromagnetic interference, but in underground system there is no chance of interference with communication line. Proximity effect, that is it is the effect of a conductor due to staying in proximity with some other conductor. So the distance between the conductors is very high in case of overhead transmission lines. So therefore here the proximity effect will not be very high. But in case of underground cables, the space between the cable is very less, so there is high chance of having proximity effect. From the point of view of application, the cost of this system is low, therefore overhead lines are used for long transmissions and for distributions in rural area. But because of the high cost of underground system, they are only used for short distance and in populated area where we cannot use the overhead transmission line. So where space is a main problem, there we will use overhead system instead of using underground cables. So here you can see there are two representation of a power system. Here you can see there is a generating station, then this entire part is the transmission part, and this last part is the distribution part. So the first picture here, it is a pictorial representation of a power system. Okay, so here we have to draw a lot of things in details for someone to understand. For the same power system that is shown in this picture, here we have drawn an electrical single line diagram, or here as it is written as one line diagram. It is actually a electrical single line diagram. Here we are using symbols to represent the generating station. For transformer, we have used this two winding symbol to represent the transformer. The conductors are here shown as there are, I have told you that the transmission is done by three-phase, three wire. So here you can see there are three wires. So here it is a single line representation. So we have drawn a single conductor representing the transmission line, and so on. Like I have told you before, in the receiving station there is a step down of voltage. Again in the substation and the distribution substation there are stepping down of transformers. So here there are different, and these square boxes represents the breaker, and these lines represents the conductors, and here it is representing as it is being grounded, and these structures as I symbols as I told you represents the transformer. So why is a single line diagram used? Single line diagram is used to represent the power system using simple symbols for each component. So drawing this pictorial representation is tough, but drawing this single line diagram for any power system is easy, and anybody who has idea of these symbols can easily interpret what this picture or this single line diagram represents. So the purpose of a single line diagram is to supply in concise, that means in brief form, the significant information about the system. So from here we get a brief idea about a system. This is another form of representing a power system, that is reactance diagram. So what is reactance diagram? As you have already seen, if I simply draw, there was a generator, then we had a transformer for stepping up, then there was transmission of power, and then before the distribution we had another transformer for stepping down. So this is the load or the consumer, and this is the transmission part. If I divide this into three sections, this is the generation part, this is the transmission part, and this is the distribution part. Okay, so there are different equipments, as you can see in the simple single line diagram that I have drawn here. There are components like generator, transformer, transmission line, which is nothing but a conductor, again a transformer, and a load, which may be motor, anything. So while drawing a reactance diagram, what we do is, reactance diagram is a simplified equivalent circuit of a power system in which the various components of the power system are represented by their reactances. So generator will have a reactance. So generator has a reactance. So this is the reactance of generator. Then the transformer, it will also have a reactance. So the transformer's reactance is given here. Then if there are different transformers there which are connected in series, it will be connected like this, and it completes like here we have the load. So this is the reactance of the motor, and then we complete this reactance diagram. So reactance diagram, why we use this? This is used for fault calculation. Why we use single line diagram? It is to represent a power system. So that's all we'll learn in this video. In the next videos, we'll be discussing the other things like transmission of power and distribution of power in details.